Good morning and good evening, everyone. I'm Jing Zhang, a researcher from Recon AIP. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guest, Professor Wang Zhangyang. The full name of Recon AIP, the Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as a research center for the Max AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance AI's fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in near future.
Oh yeah, sure. I guess I had the luxury to appreciate many good papers from your institute, and many of them about robustness. And I have always been my dad used to stay in University of Tokyo for a short period of time. That's almost 30 years ago. So I always promised to him that at a certain point of time, I'd going back to Tokyo and took photos where he used to take photos. So would I appreciate to have the opportunity when the world gets better?
Exactly. We would be very grateful you could visit us in our Nihonbashi office. University of Tokyo is a little bit far away from our center, but our center actually is in the center of the Tokyo. It's near the Zenza place. It's very nice place.
I'm aware of that.
If you can come, yeah, we will hugely welcome you. Then I'm going to introduce you to our audience. Then you can get started. Professor Zhangyang Atlas Wang is currently Jack Kilby, Texas Instrument Endured Assistant Professor in the Department of Electronical and Computer Engineering at the University of Texas at Austin, leading the Vita Group. He also holds a visiting researcher position at Amazon. He received his PhD degree in ECE from UIUC in 2016, advised by Professor Thomas S. Huang. His BE degree in EERIs from USTC in 2012. Professor Wang has broad research interests spanning from the theory to application aspect of machine learning. Mostly, he studied automated machine learning, AutoML, learning to optimize, L2O, robust learning, efficient learning, graph neural networks. His research is gratefully supported by NSF, DARPA, ARL, ARO, IARPA, DEO, as well as dozens of industry and university grants. His students and himself have received many research awards, scholarship, as well as media coverage. We sincerely welcome Professor Wang to come to our center to give his talk. Is Sparsity a good friend of robustness? Let's welcome Prof. Wang.
Thank you very much, Jingfeng. So I guess I'll take over from here. And thanks again for having me here. It's definitely a pleasure to talk about at the Recon, especially talk about the topic of robustness, since I'm very much familiar of many great researchers working in this field and personally read many papers. So it's definitely a privilege for me to share some of our recent work here, and I'm trying to cut in from a special angle, and hopefully we could have some unique things that you may also like. Okay. So I'll talk about robustness, but I'll talk about a very specialized way to look at robustness. That is how to throw the angle of sparsity. I personally very much like sparsity. I have been working with sparsity perhaps since the very start of my research career, and I always like sparsity from the classical age of comparison to the nowadays of sparse neural network. I always joke with my students that if I collect all the keywords of my own past research and do a principal component analysis of all my keywords, then sparsity is definitely my first principal component. So even I work on robustness, I will cut from the lens of sparsity. Sparsity is a very useful concept, right? People all like it because that's all comes with that help us simplify things. And many models, if you couple that with sparsity, you get more easily provable theories and also good application performance. However, if you just zoom in and look at the relationship between sparsity and robustness, actually the story want to tell you that they have a complicated romance relationship. Well, from the good old time of classical algorithms, actually people have proven that in the algorithm complexity field, sparse algorithms are guaranteed to not be stable. This is actually a PAMI paper more than 10 years ago and co-authored by my current colleague, Professor Konstantin Karameros. And he and his colleagues basically shows that in terms of algorithm uniform stability, if the algorithm for our algorithm tending to output a sparse solution is guaranteed to be less stable than an algorithm that is allowed to produce a dense solution. In other way, if we define stability or robustness equals algorithm uniform stability in traditional learning theory, then sparsity is definitely not a good friend for a robust algorithm or stable algorithm. It is guaranteed to hurt. So that seems quite depressing, right? But if you zoom in, I will tell you there is a silver line along there is a silver line along the cloud. As many people, if you work on, so if there are people, we have people here working on the algorithm theory side, you would perhaps agree with me that the algorithm uniform stability is, however, often treated as a quite a loose bound for the real world generalization and robustness. So it is, so put it another way, it means something about robustness, but it's also often not the robustness that we care for in practice. So while in that very loose notion of stability, the algorithm uniform stability, the sparsity is guaranteed to hurt, it does not necessarily mean that sparsity will hurt the robustness we care, such as the distribution, small distribution shift, adversary robustness, or many things like that. So to get a better understanding of this complicated romance, will ask us to zoom in and look at the case you're really interested. And for today, let's talk about the adversary robustness first. So now let's zoom in and look at the literature of adversary learning of deep neural networks. Well, there are a few famous papers, and here I'm just denoting two of them. Well, by Smith and the others in New York's 28, they have demonstrated that the sample complexity to achieve good adversary robust generalization is polynomially larger than the need for standard generalization. Or in plain language, that means adversary, if we want a model to be adversarially robust besides accurate, you would need more data, and it's more hungry for data. Okay, understandable, right? Because you wanted to fill in for the corner case compared to if you just wanted the average case to work better, you may need to see more examples. So that is understandable, intuitive. A counterpart conclusion comes from Nakiran and others, shows that for a robust classifier to generalize better, the robustness classifier is guaranteed to have a higher capacity or complexity. That is a counterpart conclusion, again telling us robust generalize, well, to have a machine learning algorithm generalize robustly is often more costly, which seems to be at odds with the goal of sparsity. So still, we see some depressing phenomena, but let's continue to explore a little bit more. Now let's switch gear a little bit from the theory to the application side. And on the empirical aspect, people has also explored whether we could use a smaller model and achieve the same robustness, which give us a little bit different angle. So people has been mostly exploring that in the empirical field of model compression with the goal that after compressing my model, I want my model to be as accurate on the test set, but also I want the model to be the same error resilient to adversary robustness or other outliers. And with a few literatures relatively concurrent, well, like there's a New York's 18 paper, another paper from Northeastern University in ICCV 19, and another concurrent work from my group in New York's 2019. And we basically discovered the same phenomenon. It's actually possible in practice to empirically maintain the robustness while compressing the model. So that, to me, that completes another piece of the puzzle with the theory aspect. Shows that while theoretically there exists an upper bound, that sparsity may be at odds with robustness in terms of generalization. But in practice, to compress our over-parameterized models, there is still a large room to trade off and improve the robustness without sacrificing most of the things. Here, I would need to point out that, number one, the compression, if you do not do anything specifically tailored for robustness, doing a normal compression will usually sacrifice the robustness very much. For example, if you just apply a pruning or quantization method designed to achieve the best test set clean accuracy on and then if you could please measure the test set, the adversary robustness on the same test set that usually sets. So that really doesn't come for granted. But actually, most of the algorithm, if a compression algorithms, if you couple it with adversary training, then the robustness could be easily restored. So that shows a great room. Here, I mean, because most of compression methods, such as pruning and quantization, will often followed by another fine-tuning and sometimes iteratively. So this fine-tuning process, if you use an adversary training goal rather than a standard fine-tuning goal, the robustness can be quite easily restored. So I spent some time to give you the context of from the traditional theory to deep learning theory to deep learning practice, how sparsity interact with robustness. And I'm trying to pass you this impression. This question is the answer to this question is highly non-trivial and sometimes quite context dependent. Okay, so the topic of my paper is beyond the topic of this talk in the first part is that besides those general complications, I would like to zoom in a few specific topics and zoom in a few specific aspects of robustness. And I want to look into some new problems arising from adversary training. And those adversary training issues would motivate us quite naturally to revisit sparsity. And that will be one example from such will be the first part of my talk. I'll say goodbye to sparsity for a little while and look at adversaries at the issues in adversary training. Here specifically one recent issue called adversary overfitting as another part as a background of my first part. So I guess people here more or less already knows deep learning, while being super overparameterized, often do not overfit in practice, thanks to many aspects of simplicity bias. In training and the double descent phenomenon. However, this luxury does not seem to directly generalize to adversary training. And people have observed that overfitting the training set are often overfit in adversary training. And that's quite consistent across dataset and models. And people call that robustness overfitting. This robust, as illustrated on the finger in the right. So we have a standard, while training the same model, I remember ResNet 18 here. The standard training accuracy and the test accuracy seem to be quite coincided at the end. But when you switch gear to robust training, here adversary training in PGD, I remember, the last training and testing have a large gap, which seems to be the more classical overfitting phenomenon we know. So that seems to be directly linked to a few phenomena introduced in the first page. For example, robust generalization seems to cost more data and is more complex. So in view of that, we see we are motivated to ask, can we just use a few regularizers from classical to pure or classical overfitting here in adversary training and fix this newly arising overfitting issue? And our fix to choose here is sparsity. Sparsity as a natural way to regularize the learning capacity and flexibility. We hope to use it to regularize the learning process of overparameter NNs and reduce this newly arising robust generalization gap and therefore fixing robust overfit. And our idea is to inject robustness during training and create a sparse training for robustness. It is well known that, now switching back to sparsity. It is well known that sparsity could be injected in different stages of training. The classical way for deep network to use sparsity is as post-compression pruning method. But more recently, many groups, including my own, have studied that sparsity could emerge early during the training, or sometimes it can even pruning at initialization. And also, there are many different stages you could inject sparsity. In this so in this specific work I'm about to describe is our iClear 2020 work, first authored by my student Tianlong Chen. And we go with the option of sparsity before training because we want that end-to-end regularization effect. So from head to toe, we have sparsity. That's just a naive wish. But we did not exclude the other during or after training sparsity to be same effective. We just leave it for future work. Okay. So the main idea is actually quite straightforward, I would say. It's not adding deeper paper, just a quick idea empirical paper. So we explored two options to inject the sparsity before training. One is called the lottery tickets hypothesis. So for people who never heard about it before, basically it is a method that can identify a good sparsity mask can be such that the sparsity mask, the network, the subnetwork could be trained as well as the dense network. So it is named the lottery ticket because it denotes there exists such a lucky sparse subnetwork. It's just as performant as the dense one. That's why it is called a lottery ticket. This is this method came from the best paper in iClear 2090 and is recently quite popular. So that is one thing we look at, one sparse at the initialization method. The other sparse at the initialization method is called a dynamic sparse training. Basically, it is different from lottery tickets in the sense that lottery tickets will pre-select one sparse mask at the initialization and just stick to that sparse mask. And the dynamic sparse training do the opposite way that allows you to reconfigure the sparse mask during the training. Usually, we will use some indicators such as a gradient to indicate maybe this connection during training become useless, and some other places are promising if reconnected in the sparse mask. So we will use some such indicators like a gradient to readjust the sparse mask as the training goes. And usually this dynamic sparse training would outperform lottery ticket hypothesis in the same sparsity thanks to this flexibility. What we did is quite straightforward in this paper. We basically present two variants of the algorithms, the lottery ticket hypothesis and the dynamic sparsity, and just brutally adapt them for the goal of robustness. So the first algorithm is to first identifying lottery tickets and then directly do adversarial robust training of the lottery tickets. So we call this algorithm robust bird because it directly follows our own prior work called to use lottery tickets for efficient sparse training. We call that early bird ticket. We just want to kind of use our somehow popular brand. So that's why it's named called a robust bird. And my student like those funny cartoons. And the counterpart, dynamic sparse training, is just as I said, doing adversary training, while at each time point, I only try a sparse subnetwork, and the sparse network can be readjusted by pruning useless connections and growing new useful connections. So compared to the robust bird training, this algorithm, we call it a flying bird to indicate it will change over time. And the only difference is just a sparse mask will reconfigure. We also discussed a variant of the dynamic sparse training algorithm. We call it a Flybird Plus. The only difference with this vanilla flying bird is only about we would allow you to dynamically adjust the pruning rate and the growing rate based on the gradient-based indicator signals. It is long story short, it is a more adaptive version in terms of sparsity ratio compared to this vanilla version. So that's all the algorithms. I don't claim any algorithm novelty here. I'm just make those sparse training algorithms serve robustness goal. That's it. It's really not a novel paper at all. But turned out that the finding is interesting. All those birds we play with are all good birds. So I don't want to waste your time and look at all those results. Just give you something that is quite indicative. So we have found that number one, so if you still remember in the motivating slides, I'm showing you two different curves that while for the same network on the same data set, while the standard generation is not issue, the gap is quite small. The two robust curves, training and testing, have large generalization gap. And we demonstrate that with all those three sparse training algorithms, and all of them are effective. And with them, we're able to show during robust training by enforcing sparsity in any of the three forms, we could reduce the sparse generalization. Without the Western bells means you just add sparsity, nothing changed, no early stopping, no lucky checkpoint picking. just keep changing and you don't suffer overfitting. So sparsity here indeed become an effective regularizer in different forms. And the reason, and you perhaps noticed that within this paper, we called it sparsity winning twice. That is also because with the sparse training, we simultaneously gain the benefit of efficient training because each time we only update a sparse set of active parameters. So this is indeed a something for nothing deal if you realize that. You're training a smaller network by sparse selection. And that smaller network could achieve the same good test set accuracy while without worrying about the generalization gap, no overfitting, and that does not cost any manual tuning. So that's a surprisingly simple, but a solution that works. And we have benchmarked the solutions on more data set and comparing with many different algorithms. So in general, we have found that as high sparsity as high as 80% and 90%, which means 80 to 90% of the parameters in the network was never trained at any time point. So training such a highly sparse network on adversary generalization is sufficing. So by comparing them all, we have compared two aspects. Number one, how high robustness accuracy and standard accuracy you could achieve in the trained model, because they need to first be usable, right? Before worrying about whether there exists overfitting. And we show that our algorithm, Robust Bird, Flying Bird, Flame Bird Plus, are able to achieve good, perhaps always the best, final accuracies. We find final accuracy in all the cases. One thing I would like to remind you is we also report the best accuracy, which means if every epoch I use a clean validation set to choose the best early stopping, what's the best result we could achieve? We would observe that we also have the smallest differences compared to manually picking the best early stopping checking point. We just don't manually pick and report this final result here, which shows we are pretty adaptive and automatic actually in generating the result. You don't have to watch your screen and worry about missing the sweet point. And in the meanwhile, if we compare all the results here as a testing result, if you compare testing and training, our methods are also very effective in reducing the generalization gap. And you can see that the generalization gap here sometimes can reduce for more than 20%, which means if you don't enforce sparsity, you will get 30% to even close to 40% of generalization gap compared to training and testing error if you don't specifically pick. But remember, generalization gap itself does not mean generalization accuracy or test set accuracy. Like you would probably remember, don't be actually one of our reviewers used to be confused on that. Don't be confused by just looking at this column. For example, random pruning will give you one of the smallest generalization gap. That's because its accuracy, both training and testing accuracy are pretty low. And the generalization gap is small, yes, sure, but that's useless. And our algorithm best balance between the best test accuracy plus the smallest generalization gap. That's what we pursue here. And in addition to training and inference efficiency, which is a natural benefit of sparsity. So that concluded, and as suggested by title, we see sparsity winning twice give us better robustness, better smaller generalization gap, and that comes with efficiency, no overhead at all. So that's the first part I want to share with you. I would perhaps not stop, we'll stop here for questions because I don't think I get a question from the chat box, but I will watch the chat box, and if you have any question right there, and I will answer them as I see, okay? So without further stop, I will come to my next part. By the way, I don't want to put I personally hate stacking a lot of results in paper, and I don't explain those numbers or those comparison baselines. But feel free to check our paper. We have results on CIFAR 10, CIFAR 100, Tiny ImageNet, and all those baselines we can think of. I'm just intentionally skipping them for saving people's attention. Okay, I got it. Okay, no worry. All right, so that's the first part. I'm talking about adversary robustness. And now I'm switching gear and talking about the different kind of robustness, which is certified robustness. Well, so I stole a credit from, I remember KD and Lily Wen's, not KD, I think this is from Lily Wen's slides in 19 well, seen as cert. So certified robustness compared to adversary robustness, which could be considered as an upper bound of robustness. which means I would be able to find or at least one example that could break you. Certified robustness, on the contrary, could be considered as a lower bound of the robustness. It asks, specifically, it says, if a classifier is said to be certified robustness, that means for any input X, one can obtain a guarantee that this classifier's prediction will not change within some proximity set around the point X, often represented as a L2 or an infinity ball. So that is a pretty strong requirement. And in practice, the solution also take more math like a combinatorial optimization. So the second part of the study, I want to introduce you answer to a simple question. Can sparsity also do some favor for certified robustness, given we already see empirically you can do something for adversary robustness? And the answer also short and positive. We find that pruning can also improve certified robustness, and primarily by improving the estimated bound tightness for verification. So here for background, I'll talk in next page, but for background, certified robustness is also related to bound estimation by branching and bounding algorithm. So if you know branching and bounding, you should have an idea of what I mean here by bound tightness. That means how many bounding branching point you could go through and how many remaining you could linearly relax. That's a combinatorial optimization thing. And together with because we could improve the bound as the tightness of branching and bounding algorithm, then plus the observation we already gained in the first part that sparsity could improve the empirical robustness. Overall, that gives us an all-around improvement of the overall measurable robustness, because an empirical robustness and the bound will lead to the measurable certified robustness. And then next, I will dive into detail for the statement. But for this page, I just want to take home one message that sparsity could help not only empirically the adversary robustness, but also provably the certified robustness. And now let's take a deep dive. So quick, okay, again, I'm trying to keep this quick and high level. So what factors influence the certified robustness? There are two aspects that matters. Number one, how robust the DNA is ground truth robust. So this is something, it's just like a pie. You know it's roughly something, but never accurately estimated, right? So that assumes that there is a ground truth robustness that you never know, the true robustness bound. You can only estimate, but never accurately approach that. And in practice, the level of robustness, the level of this unknown ground truth, whether it's high or low or mediocre, is mainly decided by how you train that. For example, although I don't know how actually robustness my standard trend network is, I can easily find an adversary example attack it to error rate to 100%. So I know the ground truth of robustness won't be high, right? And adversary robustness will surely help that, although I'm not sure how much it will actually shoot me precisely. So the first thing I want you to know is factor one affecting certified robustness is how high the ground truth robustness is. Although it is not directly observable, it can also be indicated by empirical robustness. So that's the first by adversary training for adversary attack, for example. So that's the first statement to keep in mind for just a minute, please. And the second point, the effect is because I also need, so certified robustness is what you can observe about imprecisely about the ground truth robustness. It's an estimation process. So there is always an error related to your observation, and how tight this and how small the error is called the bound tightness of your verification algorithm. So I could guarantee that I'm guaranteed to be within a certain range of the ground truth, although I cannot design the ground truth. And this is also further constrained by the verification time, because verification can go NP hard and then it's not practical. So the ground truth and the bound robustness are two factors affecting the actual certified robustness you can report in a paper. Then let's build the bridge between sparsity and these two major problems. So for all our statement here, we assume we're using the branching and bounding combinatorial optimization verifier, which is a state of the art. So what sparsity can help them? So the first thing, if you still remember, I was trying very hard to argue that sparsity could help empirical robustness. So we use that our previous finding to suppose that sparsity, at least from the current empirical observation, does not seem to be an enemy of the ground truth robustness of DNN because it does not seem to visibly damage the adversarial robustness. As we said, this is an indicator of the ground truth. So now let's look at the second. Assuming we are using branching and bounding verifier, there are two factors that will decide the quality of branching and bound. Number one is neural stability. Maybe I still need to give a background here, as I stated. So neural stability. So assume we only consider ReLU-based neural network. Then each ReLU could be considered as a logical operation, yes and no, right? Or all pass or all zero, right? It's the simplest case. So for any specific input, its information flow passing through the network could be considered as a hierarchical logical decision-making process, whether I go to all pass or all stop. And then if you consider that, then this will be like a branching tree that keep branching more and more, where each node will decide whether for each of the neuron, I would let the information flow pass or kill it totally. So the verified process will need, so if all those the neurons has a full possibility to be on and off, then the verifier would need to consider a total of exponential to the exponential n being the number of total neurons in terms of possibilities. Because in each of the reason I say this is because in each of the possibility, a possibility means a neuron in a specific configuration of on and off throughout the network. It will design a specific hypercube, a linear affine space in the output space. And in an affine space, it is very easy for verification because you just look at the linear function groups, right? So it is very easy to verify. The easiest thing a verifier can work on is a linear function. And the ReLU network is known to cut the output space into linear regions. And how many linear subregions? And those number of linear subregions dependent on how many neurons during the network actually have both status used on and off for different input. So if we could consider just a simplest case, assume you have such a stupid ReLU-based neural network. That is, for any input it will ever look at, all those neurons will be turned off. Means that all those neurons, its pre-activation will be always negative. Maybe you have a stupid large bias, negative, right? And in this case, just think of what output will be like. The output will be forever zero, right? Output error for any input. In this case, that's also the easiest job a verifier can do because it's only there. So, but if some of the neurons start to be on the positive range for some input, but off for the other input, that will start to divide the possibilities. And the more neurons that will have the both on and off status for the training set, the more unstable, the more cases you need to verify, which add to the difficulty of the verifier. So how many neurons will both possess on and off status for training set is considered as a neural stability. And the more unstable neurons we have in your training set path, the more verification time you will consume and the harder you will verify. I hope from a high level, it is a bit understandable. And the second thing is called linear relaxation. So notably, that means if some unstable neurons cannot be visited by the branching process, it has to be linear relaxed in order to create an overly linear function. In this case, this neuron will be upper and lower bounded by two different linear functions, and you use interval bound propagation to derive the bound. Note that when you unfold a ReLU neuron into two linear bound, upper and lower, this upper and lower bound will definitely cause to loosen bound tightness. So from a high level, we don't want a lot of unstable neurons, and we want them to be as small possible. All the neurons I could branch them, then I could verify it completely within limited time. So that's a high-level idea how the neuron stability and the number of unstable neurons is a deciding factor about the verification effect. So without saying that, how that connected to our friend, sparsity? Let's count, okay, one by one by our fingers, what sparsity can help us, okay? 0.0, sparsity doesn't help, it doesn't hurt accuracy. So scratch off. 0.1, sparsity could reduce the number of parameters. That will reduce the burden of tight bound propagation because it reduces the number of neurons, the number of variables the bounded propagation can visit. And a side effect, which was quite interesting as we discovered that, is many of existing pruning neural methods also directly reduce a number of unstable neurons. Let's recall the definition of unstable neurons. That means for those neurons will quickly change its positive and negative sign for different input of the training set. For some of the training input, it is positive. For some others, it is negative. So for pruning method, if you think of most of them, are mostly just about reducing the number of small magnitude element or some other small activation criteria. So why pruning method could help reduce the unstable neurons? Indeed, we found this phenomenon practically as a surprise. We didn't expect that. And then we realized that that actually a possible side effect, perhaps coincidentally, because, for example, think of the simplest neural method, which tend to remove all the small weights, okay? And the small weights is often correlated with weak signals in the data. The weak signal is often correlated with noise or some statistical variations, some high order variations of the data. High order variations means it often changes across the training set. So if you follow this logic chain, you will realize that many of the small activations and the small weight actually already correspond to the most changeable small component in the data. And remove them is like doing some kind of PCA to removing those unsure, uncertain part of the data and remove and keep only the certain part. And those certain parts are often the component shared by most training samples, means most training samples agree on them, and therefore most neurons will agree on the positive and negative selection and without changing too much. So that's an interesting coincidence, and I hope you agree with me that somehow makes sense, and that's a lucky coincidence for us. And lastly, if you use structured sparsity, we have GPU accelerations for network for in both feed-forward and back-forward. So that's a natural benefit of structure pruning. So with those logical chains connecting sparsity and certified robustness, here is what we found in a nutshell. As I always, I don't like to stack result. I want to give you take-home messages that may make you interested to check our paper. So number one take-home point. As we implied in this point, most off-the-shelf pruning methods, although they are not specifically designed for reducing unstable neurons, instead they are designed for reducing small activation or small weight. They coincidentally work really well for removing a lot of unstable neurons and therefore contribute to certified sparsity. This is a coincidence, but it works in practice. And we verified a lot of different pruning methods, from unstructured to structured. Second bullet, if we further designed a new pruning method that is dedicatedly removing the unstable neurons, this is stability-based pruning, which will tend to remove neurons that change size most frequently across different training samples, will contribute even better for certified robustness. And this is done by using a pruning regularizer to consider the maximum change of pre-ReLU activations given the same bounded interval width. I'm omitting the details and just trying to pass the high-level ideas. So the main idea is, as I have to advocate, yes, you get a better certified robustness. So we have measured standard robustness, adverse robustness, and this is not a variation, it's a verified accuracy. We would observe that, so compared to the dense network, whose verified accuracy is actually very low, because in the limited time, the branching and bonding just don't have time to finish a lot of verification jobs. By specification, we observe that all the pruning methods seem to improve verification accuracy quite substantially. Here we have tried two different verification library, FGSM and AutoLipara. The AutoLipa, the later one, AutoLipa, is considered more authentic in certified robustness result. So if you look at them, number one, you could find all the pruning methods seem to contribute to verification accuracy. And second, you can find that there exists some sweet point method that seem to balance really well between standard accuracy, adversary accuracy, and verification accuracy. For example, this method, IMP plus NRS loss, denote to our new pruning method target at sparsity, target at neuron stability. And we found it to achieve good balance between all the three. I don't claim this is the best, but for verification accuracy, this seems to achieve the state of the art on the more authentic AutoLipara library. This conclusion here, which pruning method is best, was not very consistent, I have to admit, in our experiment. Sometimes for this model, this pruning better. For another model, another pruning method will work the best. We didn't have a very consistent answer to offer, but the general answer we can confidently offer is pruning is a helper for certified robustness. And also, as you can see, when we switch gear from unstructured pruning to structured pruning, thanks to the current NVIDIA GPU who already support structure sparsity, when our pruning itself brings structures, the verification time T and the verification memory all get reduced. So that indeed bring observable efficiency on GPU, which is another benefit besides the verification accuracy. One step further I want to talk about is our more recent work to show that you don't actually even need to do pruning. You could reduce you could trade off between the damage of pruning because pruning will reduce element, and sometimes you still want information to have sufficient width to pass. So we have a follow-up method to create a very non-classical pruning method. What I mean is pruning method could be considered as replacing a nonlinear ReLU neuron with 0, right? So that yes, reduces stability because you are always 0. But no, it also hurt accuracy somehow because anyway you reduce the forward path of information, sometimes it hurts. So we create a new method called linearity grafting. And the idea is I don't replace the ReLU into 0. Instead, I replace the ReLU with a linear function. That is why we call it grafting. The reason we wanted to use a linear function instead of 0 is because, number one, a linear function with non-zero slope would still let information pass through and therefore create a smaller damage to network expressiveness. Number two, linear function does not add to the verification complicacy of the branching and bonding algorithm because the linear function is immediately verifiable because you can directly look at the output input level and you directly get the output level. There's nothing to certify. I'm skipping the details, and with this high-level idea to replacing pruning with a linear pruning to 0 by a new pruning, well, if you still call that pruning, to replace a nonlinear neuron into a linear function, we get an even better method compared to ourselves. So I'm skipping this table, but just to show that we can achieve a better sweet point between standard accuracy, verifiable accuracy, adversary accuracy, and time-wise, we are still fast. That concludes the second part of my talk. So if I would be happy to discuss more details, but if you are not specifically working on branch and bonding, just I'm trying to give you this technical message that sparsity helps certified robustness. It certifies faster, it certifies better, and you don't pay a lot of price in empirical robustness. What else do you expect, right? So that concludes the second part of my story. So far, my first part of the story is about adversary robustness, and sparsity helps overfitting. My second part of the story is sparsity helps backdoor. Sparsity helps certified robustness, which is provably accelerate certification and make a certifiable accuracy better. I have a third story for you. I'll try to make it quick. I realize that I'm always a very wordy person. The third aspect of robustness, backdoor robustness. So I think your institution has a lot of backdoor expert, but just for quick recap, backdoor robustness switched from the test time robustness to the training time attacks. So sometimes some malicious people will put some specific crafted symbols on a part of the training samples, and the model will behave in manipulated ways during testing when the testing samples were also attached with the same symbol, right? So I also want to explore, if I put a sparsity in training, how the sparsity could help us detect or defend against the backdoor attacks. Well, as model sparsity is already known to maintain a good romance relationship with the test time robustness, there is some good reason you could hypothesize to have to avoid the toxic artifact injected in the training dataset, right? So let's look at it. Well, there are numerous defense methods, and at least I think they can be grouped into 3 regimes: data preprocessing, model reconstruction, and trigger recovery. We focus on the third category of trigger recovery-based defenses. So the rationale behind this category is to detect and synthesize the backdoor triggers at first, followed by a second step to suppress the effect of this synthesized trigger. So you first detect what trigger it is, and then defend against that. It performs empirical well. There are a few very nice prior attempts. So for example, Hong and colleagues it shows that the backdoors are only encoded as a part of the weight, and you could directly manipulate this part of the weight if you know where to manipulate to handcraft the backdoors. Another paper, which I remember was co-authored by excellent colleagues in Riken in Europe's 2021, shows that you could also prune, which I was very happy to look at this paper, by the way, when it comes out, because it shows that you can prune a part of affected neurons, and it can remove backdoors. But with all the good words I could compliment about this paper, I have to very politely point out that in the practice, such an assumption may be too ideal for achieving if the user has no access to the benign data. Because in this paper, it assumes that you could fine-tune the pruned model, and the fine-tuning could be conducted over the clean validation dataset. You could assume to have that, but you don't always necessarily have that in practice. So this is one limitation we think of breaking. And this assumption also prevents us from understanding the true cause of the Trojan mitigation, since the possible effect of model sparsity is here entangled with the fine-tuning on the clean data. So we really don't know which actually contributed to the Trojan effectiveness, right? It could be the sparsity, which effectively regularizes. It may just as well be the clean data, because you give it good clean water to drink. So you flush out the waste water the model already drank. So you don't know which part contribute more. At least I'm not very sure about that. I'm going further with sparsity. So our proposal was summarized in our recent CVPR paper called, well, we use a word that I guess now everybody in this world knows after the terrible 2 years. This method, we call it a quarantine. And we show that you could, and you are very thinking why. I will first describe this algorithm. It's a stupid algorithm. So we will start from network, which is trained on a potential Trojan dataset. I will prune this algorithm, prune this model, and retrain on the original training set. Here, I'm giving you a highlight note. I'm on the original dataset without assuming clean validation set. Original dataset with Trojan, and I don't know where is Trojan, okay? So I prune it and retrain on the original dataset. If I don't find anything special, I prune it again and retrain again. Prune it again, retrain again, prune it again, retrain again, until I find something special. Let me tell you what is that something special I'm looking at. What we observed is, for a Trojan model, when I do this pruning and retraining, pruning and retraining, pruning and retraining, initially you will find that the clean accuracy and the attack success rate, which basically means backdoor effectiveness, you will observe that they were first both reduced to an extent, which would perhaps be something you expect anyway, right? Because the model feature get damaged, and without assuming specifically, you may expect both the clean features and backdoor features get simultaneously damaged. So both seem to be smoothly decreasing at a certain point for a certain period. But what is really interesting is after you prune again and again, and once you achieve an extremely high sparsity, extremely high here means often more than 99% of the network parameters are already pruned to zero. Usually that means pruned after more than 5 rounds, each time pruning 20%. This is an extremely high sparsity. And at some extremely high sparsity, you would, which we verified consistently in experiment, observed a sudden jump in attack success rate, while this clean accuracy is trash. I want you to digest this phenomenon for a little bit. So starting from the mediocre sparsity, when you gradually increase it, both clean accuracy and attack success rate, both clean feature and the backdoor features get damaged. But get damaged again and again and again, and at some point, suddenly, when you retry on the original data set, that you have perfect backdoor features learned, lead to nearly perfect attack success rate, while your clean accuracy is still trash. And this is what a special phenomenon I'm looking for. I call it Trojan lottery tickets. And now let me explain you the rationale, okay? So our crucial observation is that the Trojan features are significantly more stable to network pruning than benign features. And this is presumably because, not revealed by us, but some other prior work, Trojan features are mostly shortcut features that have simpler features, shortcut features that are much easier to learn for a deep network compared to the benign features. They are usually visual shortcuts. So the intuition logic chain is like this, and please follow me. First, Trojan is a simple shortcut features. They are very easy to learn. Second, these easy to learn features are still easy to learn. Even the network itself become very sparse. So rationale here is a sparse network as it goes sparser and sparser. You would perhaps agree with me that it becomes more and more unfriendly to gradient descent, right? So because it kills gradient, sparsity itself kills gradient in backpropagation. So as this sparse network becomes more and more difficult to learn from the clean data will become harder and harder to be picked up. But the Trojan may still have a good possibility to be picked up because they are particularly designed, easy to learn features. So the process I'm keeping pushing the sparsity is I'm keeping pushing the network to a point that it becomes nearly impossible to learn any clean features while it can learn nothing but this specifically designed Trojan features. And I joke with my student that our philosophy to isolate this sparse, extremely sparse subnetwork to learn Trojan is coincidental with the old Chinese philosophy where we call Shendu, and means it is very hard to preserve your cautious behavior when you stay alone. And that is also why we named this paper Quarantine, because we show that you could really find an extremely sparse network that can do nothing but do malicious things, that is learning the Trojan. And this is just an observation. And in our paper, we produce an algorithmic score based on landscape. It is called the linear connectivity score. This is inspired from deep network landscape geometry. I'm skipping the math, but we do have some more principled ways rather than just observing the curve to pick where is the lucky point. So with the key assumption we already explained, we observe that you can always observe this interesting jump, and this can be detected by our score. And our fine-tuning, as it implies, it has to rely on data with both Trojan and clean. And we use this mixture data to, which is your original training set anyway. So we use this data to show the two metrics at some point will be well separated very much. And that isolation behavior is the detection of the Trojan. So after you have, and because of our assumption, we would have such a point where this extremely sparse network, look at this number, This is an extremely sparse subnetwork of ResNet 18, I remember, of 99.97%, which means only 0.03% of elements are still non-zero. Others are all zero. So this sparse network has successfully isolated the Trojan features from benign features. And we observe that if you do Trojan trigger recovery of such a clearly isolated sparse network, the Trojan trigger recovery also become easier, cleaner, and therefore Trojan detection and defense all become more successful. So I include more results in the paper, and I believe we haven't released it yet, but should be next week, and also perform the landscape analysis to show that this so-called Trojan ticket, which are extremely sparse network that can only learn Trojan features, really have some very interesting or in other way, very bad landscape for learning. It is very unfriendly for gradient descent. And that's just like, the very high mountain, only Trojan feature can climb. So that's not usually some landscape. This is normal landscape. This is a Trojan landscape. And the gradient distribution is very, very irregular and hard to learn. So that is what we find really interesting, a bad network to help us do good things by detecting those malicious Trojans. So I will skip explaining the result. Basically, that tells us that we could reconstruct we could correctly detect the Trojan, and our recovered Trojan trigger also have small errors compared to the differences with the state-of-the-art method. Here, the stance baseline is produced by the NC. I remember neural cleaning, a standard baseline in neural Trojan, and we have more comparison in the paper, which I would rather skip. With that, I hope I am about to conclude my talk, and if I have just one take-home message to give you, that perhaps the befitting answer to the question in my title, is sparsity a good friend of robustness, is perhaps yes. And I'm saying that with a good amount of confidence. We have demonstrated its effectiveness to adverse robustness, to certified robustness, and to backdoor robustness. So I hope you can also make a good friend with sparsity. That concludes my talk, and thank you for listening.
Thank you for Prof. Wang's great talks. Basically, I have a question. I type it in the box. You can read it.
Okay, so I will read it. Okay, so first, thanks for applause for grafting paper. So I guess that's a comment. Okay, and the second one, I have a question related to Trojan lottery. The Trojan is easy to learn. When network sparse, network is representation not enough, and therefore not capture and only highlight easy feature underfitting. Can I understand this way? Exactly, yes. We find that the network capacity will come to the point that can learn nothing but trivially easy features, and the Trojan so far is constructed as a trivially easy features. That's why it's so easy to pick up and override clean features. You are absolutely right.
I see. So this basically phenomenon indicate that the Trojan feature actually is more simpler than the typical features. For example, dog and cats, that we add the Trojan this feature is very simple to learn than the salient feature like dog and cats kind of things, right? Am I right?
Yes, yes, you are correct. And I didn't make this claim. Actually, for this claim, another paper from Dr. Tian Liu's group, and I remember our archive last November had called Backdoor Learning with a shortcut. They have more expensive. They have more expanded experiment to demonstrate that this is indeed true. Yeah.
I see. Okay, thank you very much. I don't have any further question. Yeah, this is indeed very inspiring.
Thanks.
Yeah. Hi, audience. If you have any questions, you can open your mic to talk, and also you can, if you like, you can also type it in the chat box. Okay, I guess maybe not. Maybe when you have question, you can email Prof. Wang to ask him. His email is available on his website. So then this is the end of our today's seminar. We really appreciate Prof. Wang to giving us very exciting and inspiring talk. And we sincerely hope Prof. Wang can visit us physically in Tokyo in the near future when the situation is lifted. Yeah, we welcome.
That would be an honor. Thank you.
Thank you very much. Okay.
Thank you again for having me. Bye-bye.